Welcome to This Explainer. Today we are tackling Earth's absolute greatest existential threat. And we're not talking about something brewing beneath our feet or even within our own societies. We're talking about a threat from the cosmos, an asteroid impact. For a lot of us, an asteroid strike just feels like the stuff of Hollywood blockbusters, right? Something we don't really need to worry about while we're going about our day-to-day lives. But the reality is, the universe is an incredibly crowded, chaotic place, and our planet is constantly flying through what is essentially a cosmic shooting gallery. So today, we're going to break down exactly what the stakes are, what the data tells us about our vulnerabilities, and most importantly, how human ingenuity is literally racing to build a planetary shield. Okay, let's dive into this. 10,066 million years ago, a rock the size of a mountain, known as the Chicxulub impactor, slammed right into the Earth, and it hit us at an incomprehensible speed of 40,000 miles per hour. When it struck, it released the energy equivalent of 10 billion atomic bombs. Just take a second to think about the sheer scale of that energy. Everything within 1,000 miles of the impact zone was just incinerated, instantly. Earthquakes completely shattered the ground, and tsunamis towering 300 feet high drowned entire continents. Section 1. The Dinosaur Killer, or Anatomy of an Extinction. To really grasp the threat we face today, we first have to understand exactly what this specific rock did to our home. The Chicxulub asteroid was roughly 10 kilometers wide, but the collision was so violently energetic that it carved out a crater 180 kilometers across in what is now Mexico's Yucatan Peninsula. The impact actually vaporized the asteroid completely. Solid rock just instantly turned into vapor. This massive ejection of rock and dust was thrown so high into the atmosphere that it entirely blocked out the sun. For months and possibly even years, the Earth was shrouded in this freezing, suffocating darkness. And the grim result of that darkness is captured in this staggering statistic: 75%. Without sunlight, the plants died. Without plants, the herbivores starved. And without the herbivores, well, the carnivores starved. The entire global food chain completely collapsed, wiping out 75% of all species on Earth. It abruptly ended the 165 million year reign of the dinosaurs in just a matter of weeks. But honestly, here's the most chilling part of this whole history lesson. The Chicxulub impact was just one of 5 major mass extinction events in Earth's history. It has happened before, and the data clearly tells us it could absolutely happen again. Section 2. Threat by the numbers and a crowded cosmos. Let's fast forward to the present day. Just how many asteroids are actually out there near Earth's orbit? Scientists estimate there are millions. To be incredibly specific, there are at least 1 million near-Earth asteroids larger than 100 meters. But here's the critical takeaway. Out of those 1 million massive rocks, we have only officially cataloged about 1% of them. The other 99%? They're just out there, totally unseen. And that missing 99% is seriously concerning when you map the sheer scale of destruction to the size of the asteroid. A 100-meter rock wouldn't just cause localized damage. It would completely destroy a modern city and kill millions. A 500-meter asteroid? That ruins an entire continent. And an asteroid 1 kilometer or larger? That collapses global civilization entirely. Astronomers are constantly discovering new near-Earth threats every single month, which essentially means right now we are flying blind, just crossing our fingers and hoping that nothing big is on a collision course with us. And let's be totally clear here, an impact is a statistical certainty over a long enough timeline. A massive 1-kilometer impactor hits us about every 500,000 years. A 100-meter rock strikes roughly every 50,000 years. But look at the 10-meter impacts. Those happen roughly every 1,000 years. And we actually saw this recently. Back in 1908, during the Tunguska event, a 10-meter asteroid exploded over Siberia. With zero warning, it completely flattened 80 million trees. If that exact same rock had exploded over a major metropolitan area, millions of people would have died. Section 3. Anatomy of an Impact, the 10-year countdown. So, let's run a hypothetical scenario based on this data. Imagine that tomorrow our telescopes detect a 500-meter asteroid, and let's say we calculate that we have exactly 10 years until it impacts Earth. What actually happens to human civilization during that 10-year countdown? Well, it would be a pretty grim domino effect. Step 1, once the public realizes the threat, global markets would just instantly collapse. Currencies become worthless overnight. Step 2, to manage the massive panic, governments would have to declare martial law,
we'd likely see extreme resource rationing and literal bunker wars as the wealthy try to secure their survival. Step 3 is the impact itself, bringing massive land explosions or jet-speed tsunamis that just swallow coastlines. And finally, Step 4, dust and ash block out the sun, leading to global starvation. The few survivors are forced into limited bunkers, and humanity regresses to a tribal society, just struggling in the dark. Total civilization collapse.
Section 4, Earth's blind spots. Flying in the dark. So how do we actually prevent that nightmare scenario? Well, to stop an asteroid, we first have to find it. Currently, modern survey telescopes like Pan-STARRS and Atlas are scanning the night sky multiple times a week, looking for any objects moving against the background of stars. And to their credit, they're doing a fantastic job, having discovered thousands of near-Earth asteroids. But despite their power, we still have some absolutely terrifying blind spots. Now, what's really interesting about this slide is how uneven our tracking is. NASA's goal is to find 90% of those civilization-ending 1-kilometer asteroids, and notice that we're actually hitting that mark. But look at the smaller categories. We've only tracked 35% of asteroids 140 meters and larger. And for the city killers, the ones under 100 meters, we are tracking a measly 12% of them. That means nearly 90% of asteroids capable of completely wiping out a major city are completely untracked. But it gets worse. It's not just about the size of the rock, it's about the trajectory. We have this ultimate blind spot. Asteroids approaching Earth from the direction of the sun are entirely cloaked in intense glare. Our current ground-based detection systems simply cannot see them. If a dangerous rock comes at us from this daytime blind spot, we would have absolutely no warning until it literally entered our atmosphere. And if you're thinking that's just some theoretical problem, consider this number, 2,950. Back in the year 2020, an asteroid known as 2020 QG buzzed past Earth at an altitude of just 2,900 kilometers. To put that into perspective, that is well inside the orbit of the moon. It was an incredibly close shave. But because it came straight from the direction of the sun, our tracking systems didn't detect it until hours after it had already flown by. We had absolutely zero warning. Section 5, Planetary Defense Strategies. Fighting back. Let's shift the tone here, because it's really not all doom and gloom. Unlike the dinosaurs, we have human ingenuity. We have advanced physics, and we have space programs. If we can secure enough warning time, meaning years or preferably decades, we actually have actionable strategies to defend our planet. We basically have 4 primary defense options, but they all depend on one crucial factor: warning time. First, the kinetic impactor. We literally crash a spacecraft right into the asteroid to nudge its trajectory. This needs years of warning to compound that slight shift over time. Second, the gravity tractor, flying a spacecraft alongside the asteroid to slowly pull it using gravity. This is a much gentler approach, but requires decades of warning. Third, a nuclear option for last-minute threats, detonating a bomb to push the rock away, though fair warning, this comes with the massive risk of shattering the asteroid into multiple deadly fragments. And finally, the solar sail, a highly theoretical idea to wrap the asteroid in a reflective sheet to let solar winds push it, which would also take decades. Notice the trend here. Almost all of these require time. But here is where it gets incredibly exciting. Let's look at the DART mission coordinated by NASA's Planetary Defense Coordination Office. In 2022, NASA launched the Double Asteroid Redirection Test. They intentionally crashed a spacecraft into a small asteroid named Dimorphos. And it worked. It successfully altered the asteroid's orbit. This is an absolutely historic milestone for our species. It's the very first definitive proof that if we have the time and the target, we can physically move a celestial body and defend Earth. How cool is that? Section 6. The Race Against Time. Survival of the Species. The wild success of DART shows we absolutely have the theoretical capability. But to truly be safe, we need to actively track all near-Earth asteroids, and we need to have deflection rockets built, fueled, and ready to launch at a moment's notice. And right now, well, we're falling severely short on that preparation. We're essentially just waiting for a disaster to force us into action. And this leads to a fascinating debate going on right now in the scientific community about our long-term survival philosophy. On one side, you have the huge push for space settlements, colonizing the moon and Mars to make humanity multiplanetary. It is a vital goal, for sure, but it costs trillions of dollars, takes decades, and realistically, in a sudden catastrophe, it likely only saves a tiny fraction of very wealthy individuals. On the other side, you have the detect and deflect strategy. Building better telescopes and deflection rockets right now is cheaper, it's significantly faster, and most importantly, it protects absolutely everyone currently living on Earth. So, the absolutely crucial point here is funding and political will. Consider this absurd reality. We spend more on potato chips than asteroid defense. It's a striking comparison, isn't it? But it perfectly highlights a terrifying reality. The sheer lack of political urgency is literally the only thing holding us back from building a comprehensive planetary defense system. We have the brains, we have the physics, we just don't have the budget allocated to match the severity of the threat. Which brings us to our final thought for this explainer. An asteroid impact is not a question of if, it's a question of when. It is a statistical certainty. But unlike the dinosaurs, we have the science, the technology, and the intelligence to choose our own fate. So, looking honestly at our current technology and our current levels of funding, will we be ready? Drop your thoughts in the comments below. I'd love to hear what you think we should be prioritizing. Thanks so much for joining me today, and as always, keep looking up.